now evaluated two of the three performance criteria. We've discussed two of the three performance criteria that we're going to use in this class for control systems. The first was stability, second was transient response, and then the last one is steady state response. So after the transient response has settled, that is, reached steady state or approached steady state, the system may or may not be in a desirable state. Okay? So, bummer, even though you have a controller on there, you might not have the system settle down to the point you want to be at. So you might have some error that's just staying for all of time. It's not going away, which is not a very good controller if that error is significant, right? If the response asymptotically approaches any state other than that commanded, it is said to have steady state error. So if we say to go to 5 feet and it goes to 4.6 feet, that's steady state error, and it stays there. So steady state error. Or if we're, we'll stick to that for now for intuition. These arise from three primary sources. One, nonlinearities, like backlash in gears. And we're not going to really talk about that one, but it's good to keep in mind that that can happen. That is the kind of thing that's really a pain, plagues us all the time. You guys know what backlash is, right, in gears? Yeah, it's like when you go one way, you're moving something, like it's just every time you do a revolution, you get 5 revolutions through the gear train or whatever it is. But then you start to go the other way, and then there's this gapping in the meshing of the teeth, and you turn it the other way, and it takes a little bit of a rotation before it engages. And so then you lost some position control there, and you have issues arise from that. And you guys have used the have you guys used a hand driven milling machine where you move the table XY? Have you guys felt that? It's usually, you can feel it in those the backlash and the power screw.
It's more permanent in the lathe.
Oh, is it?
Like 20 pounds of slop in it.
Yeah. It's really hard to get rid of whenever you use something like that. One way to get rid of it so if you're doing a linear motion application, one way to get rid of it is to use a belt instead of a gear to do your ratio. So you could use a belt pulley system, because belts don't have that backlash problem in them. So it's good as long as you use like a timing belt that's doesn't stretch. Stretchy belts, they're not good, but timing belts are good. Okay, so that's one. Two, so nonlinear is one. Two, disturbances, like those from the environment. So if, for instance, you are controlling the speed of a motor, and suddenly, and the motor is connected up to, say, like a fan, and somebody walks by and like bumps the fan or something like that. It's gonna probably make it go off a little bit, the speed. So that sort of disturbance is something that can be an issue. It could bump it off and it might not return, that type of thing. And finally, the input or command type and the plant dynamics also have effects on the steady state error. Yeah.
So when we're talking about backlash here, say you have like a stepper motor.
Yeah.
And it's turning a gear, and there's that little bit of backlash, and it has to turn it, say, clockwise and then counterclockwise, and it's constantly doing that. Will that backlash make it go, or will it accumulate over time, or will it kind of cancel each other out since it's constantly changing?
I think that if it's like, if you have one gear one gear train and you have
Because I can
yeah.
I can rationale both of them.
Yeah, I know. I'm trying to think of
So-
which one. So you've definitely, so if you're going one way and you're tracking the correct position, so you're going left, tracking the correct position, and then say you're using an encoder on the motor, so like you're going left as much and you're tracking well, and then you start to go right, and you just accumulated error. You think that you're further right than you actually are, okay? And then you go right, and then you decide you're gonna go, so you're off this way, and then you're going to turn left again, and you're gonna think you're further left than you actually are. So I think that they cancel.
Yeah.
But what it means is
But
that
you have to go.
when you're going right, you're off by the backlash. When you're going left, you're okay. I think that's how it works. I would have to sit down. I mean,
And then as
just
long
off the
as
top
you
of my head.
shut it down at that point, and you didn't shut it down, say when it was going right, and then
So basically you'd have backlash.
So you'd have the backlash would be an issue when you're going one way, but not when you're going the other way.
But if you're going one way and then you change directions, isn't there always going to be backlash, just a slight amount, if you're changing the direction?
Yeah, well, I mean,
that's
there's,
what we're saying.
if the backlash is symmetric, then it cancels itself going the other way, I think. That little thought experiment told me that. But I would have to investigate a little further. I haven't actually thought about this before, so this was like off the top of my head. This is how I see it, but that's just part of why it's best to measure the thing you actually want to know the position of, right? So if you're trying to back out what the position is based on the encoder of the motor, then you're going to have issues if you have backlash. But if you're always measuring the position of the whatever it is, if it's a linear actuator, you want to see what is the position of the XY table or whatever. If you're measuring that position, say you could use a linear encoder that's after the gears, then you're not going to be prone to that backlash. However, you're still prone to it for your actuation purposes, and it's hard to model it, but you're less prone to having steady state errors occur.
Do you input it in such a way that basically the backlash is accounted for? Like the first blah 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 revolution is 0?
Well, yeah, I mean the major issue with that is that it's hard to predict what it's going to be when you set things up. If you can predict it, I mean, you can predict it okay sometimes, depending on the situation. It changes over time too, so as the gears wear, it changes. And for every specific machine, then it would be different. You have to calibrate it. It's not ideal, but or you could put like so if it's a completely rotational system, if it's gears and you don't have a linear situation, you put an encoder on the output of the gearbox too, so you can know where the output is. Yeah, so there are lots of ways you can account for it, but you just have to be aware of it if you're going to use gears or power screws. Those are the main ones that you got to watch out for. Okay, so we're going to focus on items 2 and 3, disturbances and command type. It's mostly going to come from, well, we're going to focus on 3, but if you talk about disturbances, it's actually really similar to the discussion in 3, so we're kind of covering 2. We're going to focus on 3. So that is our intro, and now we get into steady state error for unity feedback systems. And the first thing to to address is, why are we just doing unity feedback systems? It's actually not super common for a system to actually be unity feedback. The main reason is that non-unity feedback systems can be rewritten and evaluated in terms of unity feedback counterparts. So if you have a system that is not unity feedback, then you can rewrite it as a unity feedback system and then use this analysis. So that's the main reason for doing it. You can also derive what we're going to do here with a non-unity feedback situation too. Just a little easier to think about with unity feedback. The unity feedback means that whatever the output position is, you know exactly what that is without it going through any dynamic element. So when you make a measurement of it, sometimes there's a dynamic element in your feedback path, your instrument, that has an impact on the dynamic response a little bit. And if that happens, that is another transfer function here, and you have to, sometimes it's just a gain. A gain is really easy to deal with. But if it's more than just a gain, dynamic element, it's a little more complicated. But every instrument has a dynamic response to it. If it's an ideal dynamic response, then it's just linear. So say this is measuring a position, and it needs to give you out a voltage, and that's what you're going to compare to. An ideal one would just give you, would just measure the position and be perfectly linear with its and instantaneous with its voltage that it was put out. However, a lot of times there is, well, every time really, there is a dynamic response that happens, and it doesn't put it out instantaneously. It has some response to it, just like any dynamic system. Maybe first order response, second order response. And when that happens, it is important to take that into account. Sometimes we can get away with, if it's a really good sensor or measurement system, we can get away with just putting a gain here, which just says, oh, okay, for 2 meters, that gives us 3.6 volts. For 4 meters, it gives us 3.9 volts, whatever it is. And sometimes that happens so quickly that we don't care about how it responds dynamically. So it's just something to keep in mind, but we're going to deal with this unity feedback system now. We're going to have G1 and G2 in the forward path, where G2 is going to be the plant. Whoa, big marker. It's going to be the plant. And G1 is going to be the controller. Okay. So unity feedback says whatever comes out of the plant, we're going to try to control that. We compare it to what our command is. The difference between the command and the actual output is our error. We give that to the controller, which applies some control effort to the plant. So that's our control loop. And so we're going to consider this. First, we recall the final value theorem. I'm hoping you guys saw this. Did you guys see this in your differential equations class when you did Laplace transforms? No? So, I saw a nod out there, maybe. Anyways, it's pretty, the derivation of it's rather straightforward, but I just wanted to make you recall it instead of have to go back and derive it. So let f of t be a function of time that has a final value. So if we were to find it in the time domain, we would take the limit as t goes to infinity of f of t, right? That would give us the final value. Then, from the Laplace transform of f of t, f of s, if we were to do, think of this in the Laplace domain, then it turns out that, this is what the final value theorem states, that f of infinity, the final value, is equal to the limit as s goes to 0, not infinity, 0, of s times f of s, the Laplace transform of f of t. Okay, so that's another piece of information that we're going to need here, or that we'll at least use for this derivation. So let's consider the unity feedback system of 4.1 with command R, controller transfer function G1, plant transfer function G2, and error E. Recall that we call E of t, or its Laplace transform, E of s, the error. We want to know the steady state error, which, from the final value theorem, is E of infinity. So we want to know what the final value of the error is. It's a function of time, so we take the limit as time goes to infinity. But since we just remembered the final value theorem, it says, oh, if you want to know what some function of time is at infinity, its final value, you just take the limit as s goes to 0 of s times the Laplace transform of the time domain function, so E of s. Now, all we need is to express E of s in more convenient terms. For the analysis that follows, we combine the controller and the plant into one transfer function. So G1, G2 becomes G. Okay, just the forward path transfer function. From the block diagram, we can develop a transfer function from the command R to the error E. So we can look at this and say, this is just expressing an algebraic relationship here, right? This says that E is equal to R minus Y, right? E is equal to R minus Y. So we can write that equation first. So E of s equals R of s minus Y of s. So that's our first equation. Well, we can also write y in terms of e, right? So if we remember, we combine these to be g, right? This becomes g. So y is equal to ge. So you can say this is equal to R of s minus G of s, E of s. Now we've got E on both sides, so we have to bring this term over, factor out E, divide whatever is left to the other side. So we end up with E of s equals 1 over 1 plus G of s, which is what was left over on the left-hand side after we factored out E, times R of s, which we left on the right-hand side. So there's our transfer function from the command R to the error E. Now obviously we want the error to be 0, and that is the analysis that we're going to do. What is the error actually going to be for different commands R? Okay. So given a specific command R and forward path transfer function G, so if we have R and we have G, we could just take the inverse Laplace transform of E of s to find E of t, right? And then we could just take the limit as time goes to infinity and find out what the final value is. However, we could stay in the Laplace domain. So this is the power of the final value theorem. We don't have to do the inverse Laplace transform, which in general is pretty hard to do, right? The inverse Laplace transforms, I know you guys love doing them so much, but they're hard, right? So we try to avoid it. So we use the final value theorem. We can still find out what the steady state error is without taking the inverse Laplace transform. This is what we want to avoid. So much easier with the final value theorem. So E of infinity is equal to the limit, as s goes to 0 of s E of s, which if we plug in now our expression for E of s that we got, we get this expression here, 4.3b, and this is, right here, is as good as we can do, 4.3b, unless we have some command r. Okay, I mean we could simplify it more. We could stick g in there, but it doesn't do us any good unless we know what r is. You can't take the limit as s goes to 0 if you don't know what r is, because r is a function of s. So this last expression, best we can do without a specific r. 3 different commands are typically considered canonical. Okay, so they're the step input, the ramp input, and then this parabolic input. So there's a table on the next page, so you don't have to. You can scribble margins if you like. The first is now developed in detail, and the rest and the results of the other 2 are given below. It's really similar. The derivation is very, very similar. So first, consider a unit step command, which has Laplace transform r of s equals 1 over s. And I don't know if you remember that, but the unit step has Laplace transform 1 over s. So we know what r is, so we can plug that in and do some analysis here. So if I turn this over, we have e of infinity equals, so from 4.3b, we have the limit as s goes to 0 of s over 1 plus g of s times, now we plug in, instead of r of s, we plug in 1 over s, which is the Laplace transform of the step. And we get the s's to cancel, right? So if the s's cancel, we're left with the limit as s goes to 0 of 1 over 1 plus g of s. And this equals 1 over 1 plus kp, where we let kp equal the limit as s goes to 0 of g of s, right? So if you take the limit as 1 goes to 0, the limit as s goes to 0 of the numerator 1, that just gives us 1. The limit of 1 as s goes to 0, and the denominator is also 1, so we're just left with this limit as g of s goes to 0, as g of s as s goes to 0. When we define that limit kp to be kp, and we call it the position constant. Okay. If kp is large, the steady state error is small, right? So if kp, this denominator, kp, is large, then steady state error is 1 divided by a large number, plus 1. Still large. This is small. If kp is infinitely large, the steady state error is 0, right? If kp goes to infinity, this fraction goes to 0. If kp is small, the steady state error is a finite constant, right? So if kp goes to 0, then the error is 1. Steady state error is 1. But if kp is just small, it's some, fraction of 1. Okay. The form of g of s has implications for kp, okay? So obviously, since g of s is in kp, g of s has a factor 1 over s to the n, where n is some non-negative integer. So n could be 0, right? 1 over s to the 0 is just 1 over 1, which is just 1. So we can say that g of s always has this factor of 1 over s to the 0, 1, 2, 3, 4, 5, etc. It's in there. Since we are concerned about what happens to g of s when we take its limit as s goes to 0, this factor is of particular importance. If n is greater than 0, then if you take the limit as s goes to 0 of g of s, you're going to have a factor of 1 over s to the 1, or 1 over s to the 2, or 1 over s to the 3, etc. in there. And if you take s to 0, this is always going to blow up, blow up to infinity, right? And if it blows up to infinity, that means Kp goes to infinity. And if Kp goes to infinity, we know that the steady state error is 0, right? So this magic 1 over s term, or transfer function, could be transfer function in and of itself, is called an integrator, okay? Which is the inverse of the transfer function s, which is called the differentiator. The reason for that is the Laplace transform identities, which you may or may not recall. But s is a differentiator, 1 over s is an integrator. So putting integrators in there gives you more ability to overcome steady state error, right? So your steady state error gets smaller if you have an integrator or more integrators in there. So we'll talk about how many integrators are necessary for a given system too. So we needn't solve for E explicitly then. All we need to do, all we need to know is the command R and the number of integrators n in the forward path transfer function, g of s. And we sometimes, it's commonly called the system type. So the number of integrators in the forward path transfer function is called the system type. So if there are no integrators in the forward path, it's type 0. If there's one integrator in the forward path, it's type 1. So n, we used s the n. So n is actually the system type, then, right? So if n is 0, type 0, n is 1, it's type 1, etc. The steady state error for other commands and system type can be derived in the same manner. The results for the canonical inputs are shown in table 4.1. So before we do the example, we'll look at table 4.1 and we'll fill it in. This table took a ridiculous amount of time to put in there. It's also a very similar table in Nice. But I just want to sit back and recognize how sexy this table is. Really nice table. And I just want you guys to appreciate how nice it is. Okay, so. Thanks. Appreciate that. Okay, so here we go. We have the rows here are different commands. Okay, so unit step command is this first row. T times unit step is the ramp, right? Unit ramp command, and then we have this parabolic command. These are the three considered canonical for purposes of steady state error. Okay. So the first group of columns here is for just type n. So a system with n integrators, how does it, how can we compute the steady state error for each of these cases of command? Okay, so first we have to compute the error constant. Okay, so Kp is equal to the limit as s goes to 0 of g of s if it's a step function, which is the one we derived, right? This is the first row is the one we derived. So we'll go through the first row first. So for a step input, we derive that Kp is this, and the steady state error expression we derived is 1 over 1 plus Kp, right? For a type 0 system that has no integrators in it, the steady state error is 1 over 1 plus kp, because that's we don't get a that integrator help for type 0 system. So we have a constant finite steady state error for a unit step and a type 0 system, no integrators. Yeah.
You go over real quick how you get the type.
Type is the number of integrators. So you look at G of S and you ask the question, integrators? And the number of integrators is the type. So the number of integrators, so let me show you here. So if you had I'll give you an example, s plus 3 divided by s squared times s plus 1 times s squared plus 2. So how many integrators is in the, are in this transfer function? So it's just the bare s's. So because this is not an integrator factor because it has this plus 1 associated with it. These ones aren't either because they have, even if you factored this out, it would be s plus j root 2, whatever, s minus j root 2. This is the, if you factored this out, it would still be something s j root 2, s minus j root 2. Right? Am I right about that?
You can't do it in like the distributive form. Like if you got s plus 3 over like x to the 5th plus x to the 4th, blah blah blah. You can't just count those separately though.
Correct. So only the ones that you can factor out completely, the bare ones you can factor out completely, those are the only ones that are integrators. So if that's the case, how many integrators do we have in this one? 2. Right? So n equals 2. Good. So this,
Is that squared?
because it's that squared. Yeah. So there's 2 of them.
So if there's imaginary roots to it, it's not an integrator.
Right. Or if it's real, because like this is
Yeah, there's -1.
-1 is the root, which is real, but that's also not an integrator. Only ones that I guess you could also interpret this as being, if you were looking for the poles or the roots of the denominator, they would show up at the origin. Only ones that show up right here at the origin, s equals 0. Because this one would not contribute 1, it would contribute 1 at -1, right? And this one would be imaginary. Only the ones that show up at the origin are the ones that are the integrators.
So then I hate to go back, but in example 4.1, then there'd only be 1.
So the example that we're going to do,
Or would you have to factor out that
so that's a good question.
next term?
What do you guys think? Is that one integrator?
that equals 0.
I think it'd have to be.
Yeah, it is. It's only the ones that you can factor out. So it's pretty easy to figure out how many integrators if you just factor out as much s as you can. If there's any constant in a term at the far right, if you write it in descending order, you can't factor out any s's from it. And if you stuck in s equals 0, that's one way to test. If s equals 0 in this expression still comes out to 5, right? So it can't be, s equals 0 can't be a pole from that polynomial. S equals 0 can't be a pole from this one, because if you stuck 0 in, it would be equal to 1. If you stuck 0 into this, it would be a pole. That's why.
That makes sense.
Yeah. Cool. So that is how you figure out how many integrators you have and the type of the system. So this is for a type N system. Yeah. So this is the case. I actually have to check. Yeah, no, that's true. Okay, so type 0 system is the next one up. So if we've got a type 0 system with no integrators, and we already showed this, so Kp 1 over 1 plus Kp is the steady state error. The error constant, Kp, for type 1 system is infinite. Okay, if there's one integrator, then it's infinite. We knew that had to be true because if there are any integrators for a step input, which we derived, we knew that the error constant was infinity. That's what we derived earlier. We know that the steady state error has to be 0. For a type 2 system, 2 integrators, it's just more true, right? We have even more infinite of an error constant and a 0 steady state error. So for a step input, all you need to get 0 steady state error is one integrator. If you have no integrators, you have a finite steady state error, which is fine, as long as it's small. So it just depends on what your design constraints are. If you have a ramp command, you want to be able to follow that ramp command in steady state. The error constant, we call it the velocity constant, kv. The velocity constant, kv, is equal to the limit as s goes to 0 of s, g of s. So we add this differentiator in there, right? Which is going to cancel an integrator. That's the net effect that it has. So if you derive it out, it ends up being that the steady state error is 1 over kv. And for a type 0 system, if we were to stick a type 0 system in there that could not cancel this s, then what happens if you have a limit as s goes to 0? What happens to the error constant? It goes to 0, right? And what does that mean for our steady state error? It goes to infinity. Yeah, it approaches infinity. Because as s goes to 0, kv goes to 0, and that means the steady state error goes to infinity. Steady state error goes to infinity. The type 1 system has an integrator, right? So that integrator will cancel the s. So you're going to end up with a finite steady state error, which is, so this ends up being finite. So and if it's finite, I'll just write kv. We have to compute what it is. Depends on the transfer function. And the steady state error ends up being finite as well, 1 over kv. For a type 2 system, if you have 2 integrators in here, then one of them cancels this s, right? Then there's one left over, so when you take it to 0, it makes kv infinity, right? Which makes the steady state error, the inverse of that, 0. So for a ramp command, you had to add an integrator in there to get to a finite steady state error. So that means if you don't have an integrator in there and you want to follow a ramp, your steady state error is just going to diverge off to infinity, which is to say bad steady state error. If you have a one integrator in there for a ramp, you can make it finite. So you won't be right at the ramp the whole way, but you'll have some offset that's finite. And if you want it to be 0, then you have to have 2 integrators. And you'd probably be starting to notice a pattern here. We go up to the parabolic, you have an s squared. So if we have no integrators to cancel that, the error constant Ka ends up being 0. And once again, we have infinite steady state error. Parabolic, of course, being harder to follow in steady state than a ramp or a step. So similarly, if we have only one integrator, it cancels just one of these differentiators. And so it's still 0 and still infinite steady state error. Two integrators will cancel both of these differentiators, right? And we'll end up with a finite error constant, which is Ka. And we'll end up with a finite steady state error, which is 1 over Ka.
What's the name for, like, what was the constant name for Ka?
Oh, okay, Ka is the acceleration constant. I don't really like the names very much. I mean, it's like analogous to position, velocity, and acceleration. So that's, I guess, why people liked it. There's probably some better historical reason for it, but that's just what they're called historically.
So if you had the type 3 for the last one, it'd come out to infinity and 0.
Right. So if you end up with, if you had 3 integrators and a parabolic, you would have 0 steady state error. So this is like, you can keep expanding this. You just keep going with this, but it's just rare to think about. Well, it is less rare to think about higher types. Thinking about higher commands beyond parabolic, we might not even, we might be evaluating the system, might not even really want the commands to be parabolic, but it might be a way for us to get a feel for, if we did give it some command, how closely could it follow that command. Okay, so before we finish then, let's do this example, okay? So let a system have forward path transfer function, G. For commands R1 being 2 unit step, R2 6 times the unit ramp, and R3 7 times the parabolic input. Actually 7 halves times the parabolic input. Because I didn't put the over 2. 14 times the parabolic input. Yeah. Then, what is the steady state error going to be? So, for R1, we have didn't print this off. Let's just do it then. So for R1, well, so let's see. We said it's a type what system? So it's a type 1 system, so 1 integrator, right? So it's type 1. If we go to our table, we actually already have this in here, right? For a type 1 system, so we're in this column here, for a unit step input, we're going to have 0 steady state error. Okay? So we can just write that. For R1 gives us a E of infinity equals 0. R2 is a non-unit ramp, right? 6TUS. For a ramp input, we have, for the type 1 system, a finite steady state error, 1 over kV. You have to compute kV, which is limit of, so R1. So so I'll do kV first. So kV is the limit as s goes to 0 of s times g of s, right? Which, if I look at this g, if you plug in s equals 0, so s, the s's cancel, right? The integrator cancels with the s times g of s. And then you plug in s equals 0 everywhere, right? So we get 10 times 3 times 4 divided by 1 times 5, right? So 10 divided by, so it's 2 times 3 times 4 in the numerator. So it's 24. So this is equal to 24, which gives us a steady state error, and here is such a common mistake that will happen, is that you will forget that we're scaling this input. We're scaling this input by, it's not just a unit ramp, it's 6 times the unit ramp. So we have to scale this output as well. So it's going to be 6 times 1 over kV, which is 1 over 24. So that's equal to 1/4, right? Boom. And then R3 is easy too, because if you look in the table, for type 1 system, if it's parabolic, we're going to have error constant come out to be 0, and steady state error is going to be infinite. If you multiply infinite by 14 or by 7, it's still infinite. So we can say E of infinity equals infinity. And that is our example. So it's pretty straightforward. Any questions before I wrap up?
Yeah, where'd you get the 24 again?
Yeah, 24 came from plugging in s equals 0 here. This s was canceled by, remember the term is s times g of s, taking the limit as s goes to 0 of s times g of s. So the s's cancel. And then you plug in s equals 0 everywhere else. So this goes away, this goes away, this term goes away, this term goes away, this term goes away. And you end up with 10 times 3 times 4 divided by 1 times 5.
Oh, okay.
And the 10 divided by 5 is 2. So you end up with 2 times 3 times 4, which this is 6 times 4 is 24. Did I contrive this to be 2, 3, 4? Yes, I did that. Last night, I was like, how is the math going to be easier to do in my head? That. So, thank you, and have a good weekend, guys. Man, we went long today. I'm sorry. I didn't realize how long we went.